Hello everyone, welcome to CSEN 503, Introduction to Communication Networks. This is Dr. Amr Al-Mugi. Now we can move on to another topic in the network layer, which is the IP addressing. It's really the most important topic in the network layer. We know that the IP address is 32 bits, and we have said before that the IP address is globally unique for each device. So every device has a unique IP address that is not actually common or shared with any other device in the internet. Just to be more accurate, it is actually the interface of a device that gets the IP address, not the device itself. Why is this distinction important? If you have an end device, if you have a laptop, for example, it doesn't really matter because you're always using one interface. Even if you have Wi-Fi and mobile internet, you're always using one or the other. So at the end of the day, you still only get one IP address. However, for routers have multiple physical ports. They connect to different networks, such as the router that you see in this figure, the yellow one. Okay. Because it has several physical ports, that means it actually has several interfaces. So the routers would actually have as many IP addresses as they have interfaces. Okay, sorry about that. Will have as many the routers will have as many IP addresses as they have interfaces. Okay, so what does an IP address look like? The IP address looks like what you see in the bottom right corner of the slide. They are just 32 bits. They can be any combination of the 32 bits. And if they are 32 bits, that means that you have 2 power 32 different IP addresses, which is approximately 4 billion different IP addresses that we have on the internet. Okay. Okay, how do we write them? We take every group of 8 bits, and the notation is to convert each group of 8 bits into its decimal equivalent. So this is actually what we studied in the technical foundation course. You take this group of 8 bits, they are in binary, you convert them to decimal. So for example, this group of 8 bits is 223. All zeros and then 1 at the end is the decimal 1. And then the IP address would be 223.1.1.1 as you see here. This is how you write actually the notation of the IP address. And this is the IP address that you see on your computer, for example, if you write ipconfig in your command prompt. Okay. If you take a look at the network that we have in this figure, you might notice that some devices have a common part of their IP address. For example, take these 3 devices. They all start with 223.1.1. Only the last 8 bits are different. So it's 223.1.1.1, and then the other one is .2, and the other one is .3. And if you take with them the router interface that serves them, it is .4. So all of these devices have an address starting with 223.1.1, and then the last field changes from one device to the other. Same thing goes for these 2 devices. They start with 223.1.2. These 2 devices start with 223.1.3. Okay, and the router interface that is connected to them have also the same part common. This is actually what makes IP addresses special. IP addresses are not flat. IP addresses are actually hierarchical. It means that your IP address, your full 32 bits, not all of it specify only your interface or your device. Part of your IP address will actually specify the network that you are in. So this is actually called the network address. In this case, for example, in these 3 devices here, the network address is 223.1.1. To be accurate, it's actually 223.1.1.0, where the .0 indicates that anything can actually be connected there. It can be .1.1.1 or .1.1.2 or .3 or .4 or .anything. This network here will have a network address 223.1.2.0, and this one will have 223.1.3.0. Okay, so every IP address will have a part of it that is identifying the network, and the remaining part will identify the host. How many bits identify the network and how many bits identify the host? Basically, the number of bits that identify the network is called the subnet mask. Okay, so the number of bits that identify your network address is called the subnet mask. Why is it called the subnet mask? Because the group of devices that all share the same network address are called a subnet. So the one that I have circled here, together with the router interface that is connected with it, all of these four devices or four interfaces are all part of the same subnet. Also, 223.1.2.9, 223.1.2.2, 223.1.2.1 are all part of a different subnet. This is the second subnet. And also 223.1.3.27, 223.1.3.2, and 223.1.3.1 are a third subnet. So the figure that you see here in the slide has three subnets. It's one router connecting three smaller networks or three sub-networks. Okay. How many bits do we have to identify these subnets? We actually have 3 fields of 8, which means that we have 24 bits to identify the subnet or identify the network. That means that the subnet mask in these 3 subnets is equal to 24 bits. Okay? Just to look at it in a cleaner way, these are the 3 subnets that you have. They are the devices and the router interface that is connected to them. By the way, when you see a representation such as this one, this actually means that there is a switch here. This connection means that there is a switch. And the switch, because it's a layer 2 device, it is a transparent device. It means that is actually all the ports are part of actually the same subnet. It's actually the interfaces of the router that determine where the subnets are. So if you want to determine how many subnets that you have in your network, you have to look at the number of router interfaces. Let's actually do this exercise here for this network. We want to figure out how many subnets are connected. Take every router and disconnect the subnets or count the number of ports or the number of subnets that are connected, but don't count the same subnet twice. So if you take this router, you have one subnet here, 2, and then 3. So there are 3 subnets connected to this router. If you take the second router, there is 1. We don't count this one here because we have already counted before. So we have 1 and we have 2. So we had 1, 2, and 3 from the first router, 4 and 5 from the second router. Now let's take the third router. We don't count this one again and we don't count this one again. The only one that remains is here. So we have 1, 2, 3, 4, 5, 6 subnets. We have a total of 6 subnets in this figure. And if you take a look at the IP address, you will find that in each subnet, the network address is common. If you take, for example, this subnet, the network address is 223.1.9. And then with the other interface, this is 223.1.9.1, and this one is 223.1.9.2. Okay, if you take the subnet here, this one, you have 223.1.2 is the network address, and then the interface is either 1, 2, or 6. This is the interface ID. The subnet mask for those 6 subnets, you can actually count the number of bits that are common. These are the first 3 fields of 8. So the subnet mask, in this case, for all the 6 subnets is actually 24 bits. The notation actually is /24. Okay? That means that the subnet mask is 24 bits. Okay? The subnet mask in modern networks, ever since actually the late 90s, can be any number of bits. So you have the 32 bits in your IP address. You can take any number of bits that are there to determine actually the network, and the remaining ones will determine the hosts. Okay. So how does it actually happen in reality? In reality, what will happen is an ISP, an internet service provider, will go and purchase an address block, will purchase a chunk of IP address. How many IP addresses will the ISP buy? That would depend on how many hosts would be connected at a given time. We know that IP addresses are not typically static, they are dynamic. That means when you log off, your IP address can be assigned to someone else. So the ISP has to figure out how many hosts are connected simultaneously at any given time. What is the maximum number? Let's say the ISP determines that there is actually a maximum of 200 hosts. Okay, so I need to be able to give a maximum of 200 IP address. That means that if I have the IP address and I have the host part and I have the network part, all the devices in my network will have the same network address. What will differ among the 200 hosts is the host part. So if I have 200 hosts, how many bits should I have in the host parts? In other words, how many bits should be there so that I have a maximum of 200 different combinations? To do that, you actually have to do log base 2 of 200, okay? Just to figure out how many bits you need to represent 200 hosts. Log base 2 of 200 is actually 7.6, approximately 7.6. So obviously you cannot have 7.6 bits. So you take the ceiling of that. So you need actually 8 bits for the host part. Okay. So if you have 200 hosts, you need a minimum of 8 bits for the host part to represent them. Okay. So if you have the IP address 32 bits, okay, 32 bits for the overall IP address, and you need 8 bits for the host part. Okay, that means the remaining bits, the 200 and the 24 bits, are for the network address. That means that the ISP would go and buy a network address that is 24 bits long. That means it will go and buy a network address where the subnet mask is 24. This is how the ISP determine the size of the subnet mask that it needs to buy. Okay, I will repeat this example again. Let's say an ISP wants to support 200 hosts at the same time. It will have 200 connected hosts, and it will need to support them by giving them each one a different IP address. So it needs to go and buy a network address, which is actually a chunk of IP addresses that can support 200 hosts. How would it determine the size of the IP address space, which in this case would mean to determine the subnet mask that it would need to support the 200 hosts? First of all, 200 hosts, if you take log base 2 of 200, that is 7.6. You cannot have 7.6 bits, so you have 8 bits. That means you need a minimum of 8 bits to be able to have 200 combinations of IP addresses. Okay? If you have 8 bits for the host, that means that you would have 32 minus 8, which is 24 bits for the network part. So the subnet mask in this case is /24. That means that the IP address space is /24. Okay? If you have only 200 hosts, but you dedicated 8 bits for the host part, that means that there is a part of your IP address space that will be lost. It will not be assigned. Because 8 bits can actually support 256 hosts, but you only have 200. The problem is you cannot do 2 power 7. It is too small. 2 power 7 is only 128. You have to have 2 power 8, which is 256, if you want to support 200 hosts. In this case, part of this IP address space will be lost. In the figure that you see here, we can see a different subnet mask. This figure here shows a subnet mask that is 23 bits long. How do we do that? We take the first 23 bits, whatever they are, and we convert them to decimal. So this here is 200, this is 23, and this part here is 16, and we put .0/23, indicating that there are 23 bits in the network address. Okay. Now, the ISP would go and buy a network address of a certain size. Let's say the ISP bought a network address that is /16, meaning that you have 2 power 16 different IP addresses to assign. The host part is 2 power 16. Okay. Now, the ISP has an option either to have all the 2 power 16 devices or interfaces connected in a single subnet, or the ISP can organize this network in a more hierarchical fashion, meaning that either you have this is the GIU network, as just a single huge subnet, which is a very bad idea. It will have terrible performance. Or you can create internal subnets. Let's say you have one subnet for CS, one subnet for engineering, one subnet for business administration, and one subnet for faculty of design. Okay. How many subnets do I need? That basically depends on my functionality. So let's say I determine that I need 200 different subnets. Okay. Again, I will do the same exercise. How many bits do I need to represent 200 subnets? I will find that I need 8 bits. So I can actually take this part, which is the 16 bits dedicated for the host, and divide it even further. I will take, for example, 8 bits of that, okay, and I will create internal subnets in my network. And the remaining part will be the host per subnet. Okay, that means that if this part here is 8 bits, that means 1, 2, 3, 4, 1, 2, 3, 4. This is subnet 1, 2, 3, 4, 1, 2, 3, 4. This is subnet 2. This is subnet 3, and so on. In this subnet, I can have the host 0, 0, 0, 0, 0, 0, 0, 1. Okay. 0, 0, 0, 0, 0, 0, 1, 1. Okay. I can have the 256 combinations per subnet. So I have 256 possible subnets with 256 possible hosts per subnet. Okay, so I have created a hierarchy of networks inside my original network. So again, just to actually paint the full picture, you have first of all the network ID. This in this case would be the ID of the entire GIU network. So every device in the GIU network will have the same first 16 bits of the network ID. Okay? And then I have 16 bits for the host. I can actually leave these 16 bits intact and have one subnet for the GIU network entirely, which is a bad idea, or I can create internal subnets. Let's say I create 256 internal subnets. So I will take these 16 bits for the host and I will divide them into two parts. One is 8 bits for the subnet and one is 8 bits for the host. That means this subnet, the CS subnet, will have 16 bits that are the same with the network ID and 8 additional bits that will specify the subnet. So every device in the CS network will have the same first 24 bits. Every device in the engineering network will have the same 16 bits for the network ID, but different 8 bits for the subnet. And by different, I mean different from the CS subnet. Okay, so all the 4 internal subnets will have the same 16-bit for the network ID, but they will have different 8 bits for the subnet ID. So all the devices in the CS subnet will have the first 24 bits, and the last remaining bits for the host are different. Same for the engineering one. Okay, same for the business administration, same for the design. Okay, all the hosts in the GIU network will have the first 16 bits common, and the following 8 bits for the subnet will be different per subnet. Okay, and then the last 8 bits are different per host. All right. How many bits for the subnet do I need? Well, that depends on my hierarchy. For example, here I only needed 4 subnets. So to do 4 subnets, I use log base 2 of 4, which means I will need only 2 bits. So rather than taking 8 bits for the subnet, I can actually take only 2. Okay, and then I have 8 plus 16, I will have 14 bits for the host in this case. If I have 200 subnets, then I will need 8 bits for the subnet ID. Okay, how many bits for the subnet ID? That depends on how many subnets I want to connect. Okay. There is a different notation that is actually the one that you will use on Cisco Packet Tracer and the one that you will see in your computer to represent the subnet mask. So we've already seen /23 or /24 or /x, whatever x is. Okay. There is another notation which is basically to write the number of bits in the subnet mask as ones. So here, for example, let's say we have 16 bits plus 8 bits for the subnet. So you have 24 bits for the subnet mask. So you write them all as ones, and then you convert that to decimal. So these all ones would be 255 to 255 to 255.0. Okay, so slash 16 would be 255.255.0.0. Slash 24 would be 255.255.255.0. And then you can actually do different examples. Okay. How then are networks reachable across the internet? This is the first example that we'll see in something related to routing. We'll see routing in details in the next lecture, and this will be just the first example for something that is a little bit related to that. Okay. How does your network become reachable over the internet? Meaning that if you get an IP address, let's say it's 200.23.16.1, how does the world know how to reach you? If you are sitting at home and your Wi-Fi router or your ISP assign you an IP address, how does the remaining parts of the world know that you are reachable via this ISP and this Wi-Fi router? This is done actually through something called announcements. Every ISP will announce the IP address block that it owns. For example, here you have two ISPs. You have Fly By Night and you have ISPs are us. Each one owns a block of IP addresses that it assigns to its hosts. For example, Fly By Night has the address block 200.23.16.0/20. That means its address space is /20. That means it has 32 minus 20, which is 12 bits for the host. That means it can assign 2 power 12 IP addresses to the host. Okay, and then you have another ISP, which is ISPs are us, owning the address block 199.31.0.0/16. It's actually a bigger address block than the other one. Now let's say Fly By Night ISP divides its address space into 8 organizations. So you will see here, this is actually the 20 bits. I would like to erase that. That's okay. Okay, this is actually the 20 bits, the first 20 bits, and the remaining ones are 0. If you want to actually create, 8 subnets, that means you will need 3 bits to represent 8 subnets. So what you will do is you will take the following 3 bits, okay, and you will create 8 different subnets. This is why you will see here organization 0, which is subnet 0, has 200.23.16.0. Basically, you take all of that and you divide it or you convert it into decimal. You will see that organization 0 has the same address as the ISP itself, except that the subnet mask is different. So the entire block of the ISP, Fly By Night ISP, is 200.23.16.0/20, while that of organization 0 is 200.23.16.0/23. The subnet mask is different in this case, which is why routing information and networking information need not only the IP address, but also the subnet mask. The subnet mask is actually very important to the routers. The next organization, organization 1, will have 001 as the subnet ID. So its IP address is 200.23.18.0/23. How did we arrive at that? First, you take this block, you convert it to decimal, that's 200. You take the next block, you convert it to decimal, that's 23. You take the third block of 8 bits, you convert it to decimal, that's 18. And the final one is 0. For organization 0, this is 200. This is again 23. If you convert this to decimal, will be 16. Okay, that's why it's the address is different between organization 0 and organization 1, because the subnet ID, which is the 3 bits after the 20th bit, are actually different. And you go on, organization 2 will have 200.23.20.0 all the way up to organization 7, which is 200.23.30.0, where the subnet ID here is 3 ones. Okay. Probably there is a similar structure in the other ISP. ISPs are us, but it is not shown in the figure. Okay. Now let's say that Fly By Night has purchased, ISPs are us, has purchased all its resources, has purchased its IP address space, has purchased its routers and switches and all of that. So this acquisition allows Fly-by-Night to connect a larger number of customers and allows Fly-by-Night to serve its customers in a better way because now it has a bigger or a more comprehensive infrastructure. Okay. Let's say now Fly-by-Night wants organization 1 to be served by ISPs are us. It means that originally, when a packet comes for organization 1, it will go through the ISP of Fly-by-Night. How is that? Because organization 1, the IP address of organization 1, is announced within the address block of Fly-by-Night. Fly-by-Night, its address is 200.23.16.0, which includes everything that is /23 from organization 0 to organization 7. So if a router receives a packet that has IP address 200.23.18.1, meaning that this is actually a device in organization 1, it will be sent to the Fly-by-Night ISP because Fly-by-Night ISP has announced its address block. Now, the question is, Fly-by-Night ISP has purchased ISPs are us, which has a different address block, and now it wants, if a packet is coming to a device in organization 1, that the packet should be routed to ISPs are us, not to Fly-by-Night. It's sort of a load balancing thing. I want actually not all my traffic to come to Fly-by-Night. I want actually some of the traffic to come to ISPs are us. Now, how would this be supported if ISPs are us are only announcing 199.31.0.0? If a router receives a packet with IP address 200.23.18.1, this is a device in organization 1, which the routers know belongs to Fly-by-Night. How would then the announcements be modified such that this device 200.23.18.1 is reachable through ISPs are us? Basically, we just make ISPs are us announce the address of organization 1 along with its original block. What do we do to the announcement of Fly-by-Night? We don't change it. So Fly-by-Night will still announce 200.23.16.0/20. ISPs are us will announce 199.31.0.0/16 and will also announce 200.23.18.0/23. Now let's examine what will happen in the network. If a router receives a packet with destination IP address 200.23.18.1, this router will have a path through Fly-by-Night and will have now a path through ISPs are us. Which path will be chosen? Why, first of all, does it have two paths? It will have one path from the announcement by Fly-by-Night, which is included in this address block, and it will have now a second path from this announcement that is just made from ISPs are us. Which path will now be used by this router? Basically, we go back to our discussion of the forwarding table when we said that routers will always use the entry that has the longest prefix match, the entry that matches the destination IP address with the longest number of bits. Now you have two entries. One is /20 and one is /23. These are in the two announcements. This here is 200.23.16.0/20. And this here is 200.23.18.0/23. This one here is the longest prefix match. So if a router receives a packet with destination IP address that matches the two outgoing ports, the two paths, it will choose the longest one, which is through ISPs are us. Now, does this mean that it is impossible for the packet to be routed through Fly-by-Night anymore if this is actually the structure? The answer is no. Some routers may not be updated, and so it could be the case that some routers will still send the packet through Fly-by-Night. But once these routers are updated, once the routing tables are updated, they will now start to send the packets to the new ISP because it will have the longest prefix match in this case. Okay. A small note before we continue our discussion. Before the 90s, there was no classless interdomain routing, the subnet mask basically was of a definitive length. Basically, you have three classes of IP addresses. You have class A, B, and C. Class A is when the IP address starts with 0, and then you have 8 bits for the net ID. That means you have 24 bits for the host ID. Okay, if the address starts with 10, that means you have 16 bits for the net ID and you have 16 bits for the host ID as well. Class C, you have 24 bits. It starts with 110. You have 24 bits for the net ID and you have 8 bits for the host ID. So the biggest address space was Class A, followed by Class B, and then Class C. This was what was being used before having classless interdomain routing. So when an ISP wants to buy an address block, it has to buy either Class A, Class B, or Class C. This was very wasteful because let's say an ISP wishes to connect, let's say 300 devices. Okay, if they want to connect 300 devices, they need more than 8 bits for the host part. Okay, that means Class C is not suitable for them, so they have to go and buy Class B. Even though they only need to connect 300 hosts, they have just bought an address space that can connect actually 65 or over 65,000 hosts. So obviously this was very wasteful, which was the motivation behind classless interdomain routing. We have several actually IPv4 address classes. We have something called the multicast class that starts with 1110. Multicast is when you send a packet and the destination is not a single device, but actually a group of devices. Okay? It's like when you have a podcast, the podcast is basically broadcasted by one person, and whoever wants to listen to this podcast has to, for example, tune to a particular channel or something like that. This is multicast. It's one device sending to a group of devices. Okay. There are special IP addresses that are reserved for particular use, and they cannot be assigned to an individual host. For example, the all ones IP address, that is actually 255.255.255.255. This is an IP address that cannot be assigned to any host. It is actually called the broadcast IP address. When a device sends a packet with the destination IP address all ones, this packet is actually called a broadcast packet. This packet is received by everyone in the subnet. Okay? So when you send a broadcast packet, everyone in the same subnet would receive it. So if you have a network like this one, let's say this device sends a broadcast packet, it will be received by this one, and the router interface as well. If we take this subnet here and this device sends a broadcast packet, it will be received by this one and that one. Broadcast packets are local within a subnet, meaning that you cannot broadcast a packet in a different subnet. You can only broadcast a packet within your own subnet. And if you want to broadcast a packet in your own subnet, you create the packet and you put the destination address all once. What are actually broadcast packets used for? They're actually used for many, many purposes. For example, if you want to announce a routing table of a router, if there is an update in the network topology, for example, and you want to let everyone know, you send the broadcast packet. We will see other uses for broadcast addresses. They are actually used quite often in networks, and they are actually a very important class of IP addresses. There is also the all zeros IP address, so that is 0.0.0.0. This is also a special IP address that cannot be assigned to any particular user, and it is used when a device has just joined the network and needs to discover an IP address. So this is the IP address that it uses until it gets assigned one by the network itself. And this brings us to the next topic. How does a device obtain an IP address? There are mainly two ways. It could be static, meaning that it's hard-coded by the system. This is typically for servers and devices that wish to have a static or an owned IP address. Servers want to be accessible all the time, and they want to register their IP address in the DNS database, and so they buy a static IP address. Most commonly, our devices will get an IP address from a protocol called the Dynamic Host Configuration Protocol, or DHCP. This is actually a plug-and-play protocol that is implemented in almost every network that is basically used by devices to obtain an IP address when they join a network. When you join a Wi-Fi network, if you look at the configuration screen, it will tell you obtaining IP address. When it tells you obtaining IP address, this is actually what it's doing. It is running the DHCP protocol to obtain an IP address from the network. And so how does it work? Let's consider the network in the figure on the left. You have basically this client that is just arriving in the network and wishes to obtain an IP address. To obtain an IP address, this client has to contact the DHCP server. The DHCP server basically has a pool of IP addresses that it can actually assign to arriving clients. One note is the DHCP server need not be in the same subnet as the client. So here it just happens that the DHCP server is in the same subnet, but the DHCP server could also be here. For example, there is a mechanism to forward DHCP packets across subnets. But let's actually take the example here. So the client wishes to contact the DHCP server and the client has just arrived to the network. Now, the problem is the client doesn't know the IP address of the DHCP server. In fact, the client doesn't know anything about the network. The client has just arrived. So the first thing that the client does is to send something called a DHCP discover packet. The DHCP discover packet is basically the client looking for a DHCP server. And so how does the client send the packet if the client doesn't yet have an IP address and doesn't know the IP address of the DHCP server? Well, what the client does is they create the DHCP discover packet and put the source address all zeros. This is actually the special IP address that we just discussed. And it uses all zeros because it does not have an IP address yet. As the destination address, it puts actually the broadcast IP address all once. Okay, so what this means is the client is actually broadcasting the discover packet all over the subnet. It is sending this discover packet saying, if you are a DHCP server, please respond to me. Okay, you will see also that the transaction ID here is 654. So every discover packet will have a random transaction ID that the client will generate. What is actually the purpose of that? Imagine there is more than one client arriving to the network and wishing to obtain an IP address at the same time. They will all be using the source IP address as all zeros, and they will all be using the destination IP address as all ones. So how would the DHCP server differentiate between them? This is by the transaction ID. Every arriving client will have a different transaction ID in this case. Okay. So because it's a discover packet, a broadcast packet, all the devices in the same subnet will receive this packet, including the router interface and including also the DHCP server. All the devices that receive this packet will ignore them except for the DHCP server because this is a packet of type DHCP discover. So the DHCP server will recognize it and will reply to it. The reply is the DHCP offer. Basically, it's a packet that contains an offered IP address. The packet has the source IP address of the DHCP server, the destination IP address all once. So why is the source IP address that of the server and why is the destination address all ones? The source IP address is that of the server because the server already has an IP address in the network, and so it should use it to communicate. The destination IP address, on the other hand, is all ones because the arriving client still does not have an IP address yet, and so there is no way to actually communicate directly with the client. The DHCP offer is just sent as a broadcast. Everyone in the network, again, will receive it. By network, I mean subnet in this case. So how does the arriving client know that this DHCP offer is actually for it? Because it will carry the same transaction ID, 654, as the one that was in the DHCP discover packet. Okay. There is also in the offer this Y address. This is the offered address to the client. And with it, there is a lifetime. When the DHCP server gives you an IP address, it is given as a lease. It's not given forever. It has an expiry date. In this DHCP offer that you see in the slide, the expiry time is actually 3,600 seconds. Why is it necessary to insert actually a lifetime for the IP address? This is because typically devices will not intentionally or explicitly tell the DHCP server that they are leaving the network. the DHCP server would like to reassign this IP address at some point to a different device. And so the only way that the DHCP server would know that the IP address is available is after the deadline expires of a certain IP address and the client does not ask for a renewal. So if you get an IP address from a DHCP server and you start using it and the lifetime expires, you can actually ask the DHCP server to renew your lease. Normally, the DHCP server will actually accept that and it will not assign this IP address to someone else. However, if you leave the network, let's say you are on your Wi-Fi cell and you leave the house, so you're no longer using the IP address, you're actually switching to a different access provider. Eventually, the lease that you have with the DHCP server will expire and you will not ask for a renewal. And so you will actually, the DHCP server will take this IP address and now it can assign it to someone else. Okay. So after the DHCP offer, the client will send a DHCP request. Okay, this request basically tells the DHCP server that yes, I would like actually to have this assigned IP address. Okay. The DHCP request still has all zeros and all ones as the source and destination IP addresses. Why is that? The client cannot yet use the offer IP address from the DHCP server because this IP address can actually be offered to many clients. And so the server has not explicitly assigned this IP address to the client. This is why it still has to use all zeros and it uses all ones so that if there are other clients in the same process, they will know that this client is now actually requesting this IP address. You will notice here that the transaction ID is incremented by 1. Transaction ID is 655. The DHCP request and the following packet, which is the DHCP acknowledgement, are a new transaction. So the discover and the offer are one transaction with one transaction ID. The request and acknowledgement are a new transaction with a new transaction ID. Okay. Why is that? There might also be more than one DHCP server in the network, and so a client may actually get more than one offer. A discover and an offer is one transaction. Once a request is made, the request is actually an explicit one to the server because you see here it contains the DHCP server ID. So the client is actually asking a specific server to get the IP address that was offered to it. And so finally, the server will respond with an acknowledgement indicating that now the IP address is assigned to the client. And only after that can the client start using the assigned IP address. So it's a four-way process whereby the client actually sends a discover, gets an offer, sends a request, receives an acknowledgement, and only after that the client would start to use the IP address. This scenario is the one that is most widely used. The DHCP protocol is the one that is most widely used in networks. It is used, for example, when you sign in to your Wi-Fi hotspot at home or at the university or wherever. It is also used when you go to the mobile network, so you switch from Wi-Fi to mobile network. If you switch a hotspot on your mobile phone actually acts as a DHCP server and starts to assign IP addresses to whoever connects to it. Now, I want us actually to examine this process. Let's say this is your phone and you have just switched it to a hotspot. So you have created a hotspot, and now there are several devices wishing to connect to your phone. Okay, you will act as a DHCP server and assign IP addresses to them. However, these IP addresses are called private IP addresses. They are used only to communicate with you. You will then have a different IP address that is assigned to you by the network, which is in this case the mobile network. Okay,